This is the 6.6 notes for phase shifts. Now I do want to say that this is only going to be phase shifts for sine and cosine. I'm going to do phase shifts for cotangent, tangent, secant, and cosecant on Thursday, along with a little bit of a review on how to graph tangent and cotangent graphs. You haven't seen tangent and cotangent graphs in a while. But you have seen cosine and sine graphs as of last week. So we're going to go ahead and look at the phase shifts for things which have been reviewed more recently before we jump into cotangent and tangent graphs, which it's been a little bit since we've seen them. All right, so your horizontal shift reminder. If you remember all the way back from September, we learned about our transformations. And we learned that the general form of a transformation can be that any function which has been transformed is going to be equal to a times f of bx plus h, or minus h, plus k. And then we can rewrite this as f of x is equal to a times f of b. And we're going to factor that b out to turn into x minus h over b plus k. Now we had to do this because this is where we got our horizontal shift from. We ended up with that h over b as our horizontal shift value. So you hadn't seen horizontal stretch factors, which is this b value here, until this year. And because of that, we needed to learn the fact that it had to be factored out in order to find our horizontal shift. That if we didn't, factor that out, we would be looking at an incorrect shift value. We had to go through the process of factoring out that omega value or that horizontal shift value horizontal stretch value in order to figure out what is the actual number for our horizontal shift. If we had just stuck with up here and taken this value as our horizontal shift, it would have been incorrect. And then we still had, and I'll just use these as reminders, this was our vertical shift. And this is our vertical stretch. Now, I think I told you, and I'm not sure how much you guys would recall this, but I told you all of this is going to become a lot more important with your trig. And I don't think it's any more important than being able to do these transformations on a regular function. However, I do think it's important in the fact that the trig graphs just change a lot more based on each of these values. Your regular functions, it's more a matter of semantics. We could kind of shift everything around as we need it to make the graph look the way we want it to. While with trig functions, anywhere where we put a number, it's going to be really specific and it's really going to change the graph quite a bit. So we have to pay attention to all of this a lot more. And I go over all of this because phase shifts are essentially is all of the exact same stuff I did up there. However, they start doing it with a lot more Greek letters. This is one of those things where mathematicians start getting a little bit extra. And you might wonder why mathematicians get a little bit extra. And it's just because we want to be a little bit more specific when we're talking in terms of trig. All the transformations we've done prior have kind of been for general functions that all, even though they might not be polynomials, they sort of behave like polynomials. They all kind of base themselves off of multiplication, division, etc. Now we're looking at a whole new set of mathematics. We're looking at things where our operations that we're performing, they aren't operations of just multiplication and addition. We're taking ratios of triangles and we're creating operations to figure out what those ratios are. So it's a completely new set of mathematics and we want to be a little bit different with how we refer to things. So now I've got a phase shift formula. Functions which have a phase shift can be represented by the general form y is equal to a times the sine of omega x minus phi plus b. Now this is a little bit random in the fact that we use the English alphabet along with the Greek alphabet. We use A for amplitude. Don't ask me why we decided to use B for vertical shifts. That's just what our book does. We'll stick with it. Now we can also rewrite this as y is equal to A times the sine of omega x minus phi over omega. And I should have another parenthesis here in front of this x and behind that phi over omega. It's the same thing as what I did up there where I factored that horizontal stretch factor out. We have A times omega times x minus phi over omega plus b. And I need a sign here, don't I? So this is y is equal to A times the sine of omega. And this is exactly what I just did on that previous slide where I factor out that horizontal stretch factor. The same thing is happening here. It's not a horizontal stretch factor anymore because that omega does have, it impacts our period. So it does have the same effect as a horizontal stretch factor where it's going to kind of shrink or widen our graph. It's going to change the wavelength of our graph. So I still need to factor it out to apply to my phase shift. Now, omega has to be greater than 0. Our phi is going to be the Greek letter phi, and these are real numbers. The graph will be a sine curve with an amplitude of the absolute value of A. As omega x minus phi varies from 0 to 2 pi, one period will be traced out. So this is a formula to figure out where my period starts and ends. So your period starts at omega x minus phi is equal to 0. And I'm actually just going to put whatever is inside the sine function and set it equal to 0. Doesn't matter if I have a plus phi or a minus phi. I'm just going to take whatever's inside that sine function and set it equal to 0. Just like I'm going to take whatever is inside the sine function and set it equal to 2 pi to figure out where it ends. Now these formulas over here are given, but it only works if you're subtracting phi in your equation. When we start looking at like if I have a shift to the left and I'm going to add my phi, that's going to change where my start and stop is. So I'm actually just going to set whatever's inside my sine or cosine function in order to figure out what happens with my start and stop of my period. And we got some phase shift formulas here. Again, we can see this is already what I wrote up top, where I factor out the omega from that x minus phi. So now I have A times the sine of omega times x minus phi over omega. And this will allow me to see what my actual phase shift is when I factor out this omega. If I just list phi as my phase shift, I'm going to get things a little bit incorrect here, and that's not okay. We call the number phi over omega the phase shift. You've already heard me say this a million times, but this is where the book finally breaks down and says phi over omega is the value of our phase shift. And what is a phase shift? That's a horizontal shift, but again, we create a new terminology when we're in trig graphs because we're just looking at something a little bit different for trig. So now we have all of this information. We've already learned this. The same thing applies for if we have an y is equal to A times the cosine of omega x minus phi. My amplitude is A, my period is 2 pi over my omega value, and then my phase shift will be phi over omega. The phase shift is to the left if phi is less than 0, and to the right if phi is greater than 0. And this gets really, really tricky the way the book writes this, because we have to think about the fact that this is minus phi. So it's going to be easier if you have omega x plus phi. This is to the left. And then omega x minus phi is to the right. And that is based off the fact that since we're talking about a negative phi value, when we have that omega minus or that omega plus, that shifts whether we're moving to the left or right. So if I have plus phi, that's a shift to the left of phi over omega. If I have omega x minus phi, that's a shift to the right of phi over omega. All right, I realize that there's a lot of verbiage here. I've thrown a lot of new Greek letters at you. I've thrown a lot of statements. We've thought a lot about this theoretically. And if you haven't followed so far, that's okay. This isn't an easy thing. You haven't seen factoring out your horizontal shifts until September of this year. You haven't done anything like this in Algebra 2. And now I'm asking you to do it with trig, this brand new subject, which you only got a really, really brief intro to last year. And we've had, unfortunately, a pretty interrupted learning scenario this year, which isn't ideal. However, we're going to be able to get through this, and when you start looking at the examples, it's all going to make a lot more sense, I promise you. So for example 1, find the amplitude, period, and phase shift of y is equal to 3 times the sine of 2x minus pi, and then graph the function. All right, so let's go ahead and look at this. I'm just going to go through and identify my amplitude, period, and phase shift. So right under this, I'm going to go ahead and write out y is equal to a times the sine of omega x minus phi. And I'm really going to be able to quickly say my pi is phi. That's fun to say. 2 is omega, and 3 is my a. And then I can start thinking about these formulas I have up here on this previous slide, the ones that I just highlighted. I can go through and say my amplitude is just going to be the absolute value of positive 3, which is just 3. I can say that my period is 2 pi over omega. Omega in our case is 2. That reduces, and I'm looking at a period of pi. And then finally, my phase shift is phi over omega, which in our case is pi over 2. And then I have minus phi, so that means that it is to the right. And I'm even going to put that minus pi, and I'm really going to highlight that minus aspect to let you know that's how I know it's to the right. Now, I'm looking at the graph, and you might be saying to yourself, all right, this is all well and good. I know my amplitude. I know my period. If it was just an amplitude and period shift, I've done enough of these from previous homeworks and previous notes that I know what I'm doing now. But I have no clue what's going on with this phase shift, Mr. Yehlen. What do I do? Well, this is where I'm going to go back up to these formulas I gave you in the notes. And again, it says omega x minus phi, omega x minus phi, and that's really making sure that you know the sign. I'm going to make a note here. Just plug in what's ever inside sine. Or inside of the function. And that's going to make a lot more sense when I get to the second example when I work with cosine, because this is going to look frighteningly similar to that first example, but that's because I'm subtracting phi. I'm not adding phi yet. So I'm going to figure out what are my starting and ending points from my period, because once I know that, my life is going to be a lot easier. Let's change my color for that. I'm going to say that my period start. I'm going to take the end side of that function. I'm going to say 2x minus pi is equal to 0. I'm going to solve for this. 2x is equal to pi. X is equal to pi over 2. So my period is going to start at pi over 2. And now my period end, 2x minus pi is equal to 2 pi. 2x is equal to 3 pi. X is equal to 3 pi over 2. I'm going to stop and do a quick mental check. My period is pi. And then I look here and I say, oh, well, this works out pretty well for me because there is pi radians between these. So that checks with the period. My period is pi. I have a period that starts at pi over 2. It ends at 3 pi over 2. I can just go through and think of it that way. Wonderful. I've done that. I'm happy with that. Now, one thing that I want to note is this is the sine function. I'll change my color here. So this is a sine function. And there's no vertical shift. Therefore, the period still starts at y is equal to 0. So we learned that with my sine function, my period would start at the point 0, 0 if I was just looking at y is equal to the sine of x. Well, I've done a bunch of things here, and I've shifted where my period is going to start and end. However, what I have not done is any vertical shift. So that means my period still has to start at y is 0. I'm changing the x value where that period starts, absolutely. However, that y value remains unchanged with that vertical shift. So now that I know that my period is going to start right here at pi over 2. And then I know that that period is going to come back to where the sine period has to come back to. It's got to be back at that point, y equals 0 by 3 pi over 2. Well, now that I'm here, I'm going to think back to that sine and cosine notes that I did last Monday or Tuesday. And I'm going to say to myself, all right, I'm going to break this down in quarters. It goes up to the top of its amplitude, which is at 3. We'll scale this by ones. So it's going to go up here to 3 because we have that amplitude of 3. It's going to come back down to 0, and then it'll go down to negative 3 because we've shifted that amplitude value, and this is how the sine function operates. I still have all of the quarters of my sine graph. I'm going to then just go through and keep up with the pattern, up 3, back to 0. I'll work over here, down 3, back to 0, up 3, back to 0. Down 3, back to 0, so on and so forth. I'm going to fill out my entire chart because I'm really dedicated to making this entire thing filled. And then from here, I'll just draw my sinusoidal wave. Now, the beautiful thing about trig and about a lot of math is there's some math that checking yourself, it takes a while and it's a little bit of an arduous process, but it's still advised. With trig, I can do a couple really quick mental checks to see if everything's adding up. So first thing I'm going to do is I'm going to highlight one period. I'm going to highlight the period where it should theoretically start. I'm going to look here. That's the full shape of the sine graph. I'm pretty happy there. I've got a full period happening. And I look and I say to myself, oh, cool. My start is at pi over 2. My end is at 3 pi over 2. That's what I solved for. That's what it should have been. My distance between these is pi radians. That's good too, because now I'm saying to myself, all right, I've got the same starting point from my period, which I listed. I have the same ending point from my period, which I listed. And I have that pi radians for my entire period. My sine is going up to its peak, it's going down to its valley, and it reaches the axis, or hits 0 again halfway in between those two values. My quarters look good, my sine graph looks good. I've got a lot of indications here telling me that I have more than likely correctly graphed this function. Now, granted, all of this comes from a pretty deep understanding of what sine looks like and having practiced this a lot, but these are the quick mental checks you can go through. Might not always turn up. You might have to check back to notes. You might have to double back. But just because you graphed a function doesn't mean we can't stop and think about what that graph looks like and whether or not we've gotten it right or wrong. All right. My second example here is pretty gnarly. I've got y is equal to 2 times the cosine of 4x plus 3 pi plus 1. Wants me to do the same thing as I was asked of in example 1. I want to find my amplitude, I want to find my period, I want to find my phase shift, and then I want to graph this. So let's go through and just start listing our values. Again, I will write below y is equal to a times the cosine of omega x plus phi. My amplitude here is the absolute value of 2. So my amplitude is 2. My period will be 2 pi over omega, which in our case is 4, so I'm looking at a pi over 2 period. My phase shift is going to be 3 pi over 4 because it's phi over omega. I can't simplify this anymore. And this is going to be to the left because I'm adding it. Now, technically speaking, if you were to ask like a real hardened mathematician, I should have gone through, I should have put the negative in front of my phi. I should have stated that this is negative 3 pi over 4 of a phase shift, so that's how I know I'm moving to the left, etc., etc. But I'm not going to get into all of that. I can tell you that I'm moving from my origin. I'm going 3 pi over 4 radians to the left, and I can do that based on the sign here. So I'm not concerned with exactness. I'm much more concerned with correctness. One last thing that I'm going to add in here is that I do have a vertical shift. Up 1. It's not asked of me, but I do want to note that is here. Again, not asked me in the question, but I might as well write that information down while I'm thinking about it. Now I'm going to figure out where my period starts and ends. So my period will start at 4x minus 3 pi is equal to 0. Plus 3 pi, plus 3 pi, plus 3 pi. I apologize. So I'm going to add 3 pi. I'm going to say 4x plus 3 pi is equal to 0. I'm going to take what's inside of that cosine. I'm not going to try to figure out omega x minus phi. I'm not going to try to figure out if my phi is positive or negative, all of those. I'm just going to take what's inside the cosine and set it equal to 0. 4x is equal to negative 3 pi. X is equal to negative 3 pi over 4. So I now know that this is where my period has to start. To figure out where my period ends, again, I'm going to take 4x plus 3 pi, but now I'm going to set it equal to 2 pi because that's where a normal period would end. I'm trying to figure out how this shifts within this cosine function. I'll subtract 3 pi from both sides. I get 4x is equal to negative pi. I get x is equal to negative pi over 4. Quick check of myself. This is separated by pi over 2 radians. This checks with the period. So my period should be pi over 2. My start point and end point still there. So far I'm feeling pretty good about this function. I have a start point and an end point which matches up really, really well with my period. And now I need to go through and graph it. This is going to be kind of ugly. We haven't really looked at graphs, especially when I'm given a trig graph like this with all these radian values of how to estimate it. This graph isn't going to look perfect, and it's okay that this graph isn't going to look perfect. I'm going to expect you to show me kind of a general knowledge of what the graph looks like, and that's about all I can expect of you. We're still going to scale our y-axis by 1s. First thing I'll do is I'll draw this fake axis. Again, I showed you this. At this point, you've seen it now on the video answer key for that graphing sine and cosine review worksheet, as well as your 6.5 part 2 notes. I showed you kind of my fake axis method of a vertical shift, especially when I'm thinking of sine or cosine. So what I'm going to do at this point is I'm going to treat this as my new x-axis. This allows me to just employ my entire shift upwards without having to think too much about where does each point have to go. So now I'm just going to treat this as my x-axis. So I'm going to redo all of this. Now, My period is going to start right here at negative 3 pi over 4. So I'm highlighting negative 3 pi over 4. That's where my period starts. The cosine period starts above the x-axis. It doesn't start on the x-axis. And my amplitude here is 2. And it is a positive 2, so that means I still start above. So I go ahead and I put my point here, starting 2 above where that x-axis goes. Oh, wrong spot. Starting here, 2 above where that x-axis goes. And then I know that I've got to be back at that point 2 by the time I'm at negative pi over 4. This is pretty ugly and it's not going to be the prettiest. But since I know my quarters well, I know that I've got to be 2 below this x-axis, halfway in between it, and then it's got to reach 0 each time in between. So I've got all of these points now. And then I can go through and I can draw this cosine function. And you can see that this takes a little bit. It's kind of hard to go through. You can see I put that point in the wrong spot, but then I went back through, I checked myself, and I said, oh wow, I put that point in the wrong spot. I'm going to put it back where it should go. And now I have my cosine function. I've got a full period here. It has that starting point of negative 3 pi over 4. It has that final point of negative pi over 4. I've got a period of pi over 2. Everything here looks beautiful. Now I do want to I'm just going to copy and paste this. This is going to be a copy pasta job here. I don't want to make my life too hard of going through and repeatedly drawing all of these periods over and over. And again, I'll try to make these line up. And I'm not going to fill out my entire graph here because this time this is one of those things that would just be foolish of me to try to make sure every single point works. But there you have it. I went through, I figured out where it starts, I figured out where it stops, I shifted my axis, I put my amplitude in. This is what 2 times the cosine of 4x plus 3 pi looks like. Now this does all seem very complicated, but there is a series of steps you can follow, and you can go through, you can ask yourself some questions, you can ask yourself, what did I find my period to be? Does it look this way on the graph? What did I find my phase shift to be? Where should my starting point be? Where should my final point be? Does this all make sense? And it all looks pretty good to me. I'm confident in this graph, and I can tell you for sure that it's right. This is your homework for tonight. I'm going to answer 2 questions on that homework answer key, which is about 40% of your homework tonight. So you should have more than enough information between these notes and these 2 questions. And again, questions earlier rather than later. Reach out to me and we can start working on them. Have a great night.